Hi guys, in this question, we are given that the width of the square is 10 and the radius of the red circle is 3, and we are asked to find the radius of the blue semicircle. To solve this problem, we can first consider the width of the square as a constraint to the enlargement of the blue semicircle. So, it is a good approach to set up equations in terms of the radius of the blue semicircle and the width of the square, in other words, 10. For convenience, let's quickly give some names to the important points in the diagram. For the intersection point of the red circle and the left border of the square, let's call it point A. For the intersection point of the red circle and the bottom border of the square, let's call it point B. For the center of the red circle, let's call it point C. For the intersection point of the red circle and the blue semicircle, let's call it point D. For the projection point of point D on line AC, let's call it point E. And by the definition of projection, angle CED should be 90 degrees. For the center of the blue semicircle, let's call it point F. For the top right corner of the square, let's call it point G. For the projection point of point D on line FG, let's call it point H. And by the definition of projection again, angle FHD should be 90 degrees. Also, let's denote theta as angle CDE. As lines CD and DF are both perpendicular to the tangent line crossing the intersection point of the red circle and the blue semicircle, we know that CDF is a straight line. Then, since line AC and line FG are parallel to each other and CDF is a straight line, we know that angle ACD equals angle DFG. So, as both angle CED and angle FHD equal 90 degrees, we can subtract them from the left side and the right side of the previous equation respectively. On the left side of the equation, as angle ACD is an exterior angle of triangle CDE, angle ACD minus angle CED yields angle CDE. And on the right side of the equation, similarly, as angle DFG is an exterior angle of triangle FDH, angle DFG minus angle FHD yields angle FDH. Therefore, angle CDE equals angle FDH, which means we can also denote theta as angle FDH. Okay, from the horizontal perspective, we can notice that AC plus CE plus HF plus FG equals the width of the square. And from the vertical perspective, we can notice that BC plus ED plus DH equals the width of the square. So, we have got a set of two equations. To solve these equations, we should notice that AC, BC, and CD are all equal to 3, as they are radii of the red circle. Also, by denoting R as the radius of the blue semicircle, we can express both DF and FG as R. Then, we can express CE, ED, HF, and DH in terms of R and theta. CE equals 3 times sine theta, ED equals 3 times cosine theta, HF equals R times sine theta, and DH equals R times cosine theta. By plugging what we have got just now and 10 for the width of the square into the set of equations, we can convert the equations to 3 plus 3 times sine theta plus R times sine theta plus R equals 10, and 3 plus 3 times cosine theta plus R times cosine theta equals 10. Then, after rearranging the terms, we can get sine theta equals the difference between 7 and R divided by the sum of 3 and R, while cosine theta equals 7 divided by the sum of 3 and R. Next, by squaring both sides for each of the two equations, and then add the results of the two equations together for the left side and the right side respectively, we can get sine square theta plus cosine square theta equals an expression in terms of R. And since sine square theta plus cosine square theta equals 1, we can finally get an equation involving only R. After solving that equation, we can get R equals 4.45. And that's the answer.